So last time we quickly went over inverse trigonometric functions. So let us again quickly go over inverse trigonometric functions and solve some serious looking problems. Now that you are seasoned calculus students, you know that there is nothing serious or difficult in calculus. If you take the derivative, everything breaks down. Okay, so that's what we'll do. So more inverse trigonometric functions. Let me remind you that the general rule to keep in mind is always y is equal to f inverse x if and only if x is equal to f of y. Okay? So you shift the places. So this means, among other things, that if you want the derivative, you work on this side. So this suggests two things. Well, it suggests many things, but I can think of only two at this moment. One, if you need y prime, you work with x equals f of y together with chain rule. Okay, so this is the first trick, if you like to call it a trick. The second thing is if you plot y equals f inverse x and y equals f of x on the same chart, on the same, okay, let's say chart, whatever that means, then the graph of, we are interested in the graph of this, the graph of f inverse x is reflection of y equals f of, reflection of the graph of y equals of the graph of y equals f of x across y equals x line. Okay? So this is not magic, because if you have a point A, B on, okay, so generally we denote this graph of y equals f of x, graph of, okay, then it means that f takes this number and gives you this number. So f inverse will take this number and give you this number. So this is the domain of f inverse. So BA is on graph of y equals f inverse of x. Okay, so you just shift the places of these things. Shifting the places of these things means that you are reflecting everything across the line. Y equals x line. Okay, so if this is x, this is y. If this is the y equals x line, okay, so let's do it this way. So what's happening is this thing. If this point is A, B, then this point, this is perpendicular, these sides are equal, this is BA. Okay, so easy stuff. Okay, so we attack the graphs of inverse trigonometric functions from this, using this observation. And when we need the derivatives, we use this one. The reason why inverse trigonometric functions is useful is that the derivative of f can still be expressed in terms of f. Okay, derivative of sine is cosine. Cosine can be written in terms of sine. Okay, derivative of secant involves tangent. Derivative of tangent involves secant, and secant and tangent can be written in terms of each other. Okay, so we exploit this fact, because here you see when I take the derivative, this side will give me 1. Here, this will give me f prime, and I can still express f prime in terms of f, and then I'll have y prime. Okay, so I can solve for y prime in terms of f. when you write something in terms of f, it means that you are using x. So so on this side, we managed to write the derivative of y in terms of x. So that's why inverse trigonometric functions are useful. We can explicitly write down formulas. So let's quickly go over sine, tangent, and secant. Last time I hurried here about secant, so I didn't finish it. I'll finish it now. Okay, so let's start with the sine inverse. Okay, so y equals arc sine x. Okay. So the domain of this, we will discover the domain from the graphs. I will not immediately write it here. So, okay, so if this is x, this is y, so sine is between 1 and minus 1. Okay, so here you have pi over 2, right? Minus pi over 2. And here you have plus pi over 2. Okay, so let's use a different color. Maybe that will be nice. So the graph starts like this and goes like this. So it is horizontal here. So when you reflect it over, it will be perpendicular. Okay. Okay, so let's now, so this is y equals sine x. Now we want to reflect this about y equals x line. Okay, now this line, so what will happen? Well, you see, where will this line go? This line will be reflected to this line. Okay, so let me do it this way. So here I have okay, so here I have minus 1. Okay, so this thing, draw this picture on a transparent slide, okay, and then flip it over like this, and you will, well, you have to do some magic. So this is minus 1, this is plus 1. This is now this, when you reflect this, you see this comes here. X and y axis changes places as we did there. So this is minus pi over 2. And here I have pi over 2. Okay. So it was like this when I flip it. Okay. So this piece will be like this. So it will be, the tangent line will be perpendicular. So it will start from here. It will start from here and it will go like this. Okay. So now we know from here or here that since the range of sine is from minus 1 to 1, arc sine, we also see from here, takes in its domain, takes as source from minus 1 to plus 1. So this will make sense for x between plus and minus 1. So last time we calculated its derivative using that observation. We found, okay, let me just write the derivative. Y prime, okay, so here now this is y equals arc sine x, okay. And y prime for this picture is, what was 1 over square root 1 minus x squared, okay. We checked that, first of all, we checked that this is always positive. Here we had to make a choice about whether we should use the negative square root or positive square root. The graph is increasing, so we take the positive square root. And we will have 1 over 0 when x is plus or minus 1. Well, that is in accord with what we were expecting. At this point, the tangent line is vertical. Okay, and also here vertical. So this formula will give me meaningful numbers when x is strictly between minus 1 and plus 1. Okay, so you see everything follows from common sense. The only trick, if you like to call these things, is that when I'm drawing the graph, I make this observation. So I just flip it around y equals x. And when I'm trying to take the derivative, I take the derivative on this side and then try to write everything in terms of x. Okay, so when we do it with the sine, we obtain this one. Cosine will not be much different. So let me quickly write cosine. Generally, we don't use cosine because the place where you use these things by hand is in integration techniques. Okay, so you see that we didn't know how to integrate such an expression up to this point. Okay, so this enriches our repertoire of antiderivatives. With cosine, we don't expect anything new because the graph of cosine is exactly the same thing, except that you have to shift this a little bit. And sine and cosine satisfy a symmetric relation with respect to each other. Square of sine plus square of cosine is 1. So it doesn't matter which one you choose, you'll obtain exactly the same formula. So the derivative will be similar to this, except that maybe we will have a sign depending on which arm of cosine you choose to invert. Generally, in the books, we invert the following one. So this is y equals arc cosine x. So first we'll look at which part of cosine we want to invert. So it is this part, x, y. So this is the graph of y equals cosine x. Okay, so this is at 0, it is 1. At pi, it is minus 1. So this is pi over 2. Okay, so when you reflect this, you see that this part, y-axis become x-axis. So this point comes here. Okay, this point goes here, so this point goes here. So when you reflect it, the graph will be something like this. Okay, so let's do that. Yx, so it will come, yes, it will come, it will cut this over here, and it will end up here. So I don't need this part much. Let me erase that. Okay, so it will be something like this. Okay, so this is y, this is x, this is y equals arc cosine x. Okay, so this is pi. This is minus 1. You see, this is minus 1, this is 1, this is pi over 2. Okay. So arc cosine again is on the domain from minus 1 to plus 1, minus 1x 1. And again, we expect that the derivative will not exist algebraically at the endpoints because there the tangent line is vertical. Okay, so we don't assign a number to the slope of a vertical line. We just observe that it is vertical. Since, as I mentioned there, since cosine and sine both are satisfying a symmetric equation, when you solve one for the other, you'll get exactly the same thing. So y prime should be again plus or minus 1 over 1 minus x squared. Okay? As in the case of sine, we have to decide which square root we are taking by looking at the graph. The graph is decreasing, so we have to take the minus sign. Okay? And again, we write our observation that at the end points, this expression will not give us anything. For the end points, we have to consider the graph. Okay, so this was cosine. Let's do tangent quickly again. Okay, so here we look at tangent x. So the graph of tangent x is probably the easiest to understand. At minus pi over 2. Okay, so we have these vertical asymptotes. The function comes from minus infinity goes to plus infinity. This is y equals tangent x. So we just flip this around. When you are flipping this around, remember that this x will become y. So something perpendicular to x will be perpendicular to y in the next case. Okay, so it will be this like this. So this part goes to plus infinity, and the graph of this will be asymptotic to this. So the graph will be like this. Okay, just picture this in your mind. So let us draw that. This is x, y. So this asymptote becomes this asymptote. This is pi over 2. This asymptote, you see, when I flip this around, so it was like this, it will be flipped here. It will be this asymptote minus pi over 2. Okay, so this thing comes from minus infinity. It goes like this to plus infinity. This is y equals arctangent x. Okay. And we calculated the derivative of this, and we found that y prime is equal to 1 over 1 plus x squared. Okay. So we see that the derivative is always well defined. Okay. And here tangent x, remember here is that between minus pi over 2 and pi over 2. Okay. But for arctangent, and it takes every value. So when you go to inverses, the domain of this becomes the range of this. The domain of this is this interval. So that's the range of this. And the range of this becomes the domain of that. The range of this is all of the R. Okay, so wherever you put your finger on the y-axis, there is a point of the graph. So that's in the range. So here x is in R. Okay, any x will do. So you see that when x becomes very, very large, this becomes almost 0. So that explains the graph here becoming asymptote. The slope of the graph becomes almost horizontal as you move in this direction. So that explains, so this the derivative formula explains the graph correctly. So we are satisfied. So let us do the second one, which we did not finish last time. Okay, so that is, let me see, I have the picture here. So this is what the numbers are. When I get confused, I get 4. Okay. Y equals secant x. Remember that this is 1 over cosine x. So let us start with the graph of cosine x. Okay, so x, y, and say which part. Okay, so I'll use again this part. So I won't draw all of this. So let us take this part. This is y equals cosine x. Okay, so this is 1 at 0. At pi over 2, this is 0. And at minus 1 pi. At pi, it is minus 1. Okay, so this is y equals cosine x. So we have this. This is going to be a vertical asymptote later when I take 1 over cosine x. Okay, so now let us look at this. Okay, I'm not using the left-hand side, so I'll draw it like this. X, y equals 1 over cosine x, which is denoted by cosine x. So let's say this is 1. Okay, so this is 1 and this is minus 1. Okay, so let us look at what happens in this interval. So let me also put here pi over 2. And let us take these like this. And this is going to be pi. No, I'm not doing this correct. Oh, yes, I'm doing this correct. Okay. No, I didn't take the inverses yet. I'm doing just 1 over. Okay, so 1 over 1 is 1. The curve starts here. Okay, then it decreases down to 0. 1 over that increases up to infinity. So it is this part, and it becomes asymptotic to this line. Okay, so let us do this like this. Y equals this. Okay, and now on this interval pi over 2 to pi, here it is 0, so 1 over that will be infinite, and it will go up to 1 over 1, okay, 1 over minus 1. So this is minus 1. You see it is always negative here, so 1 over that is negative. Okay, so the curve will come like this, and it will hit here. Okay, so this is second. Now I want to invert this. So it is easy. Now I just consider the line, consider this line through the origin, y equals x. Just flip this around and see what happens. Okay, so that's what I'll do now, hopefully. Okay, so arc second, or okay, here is my arc second. So I have this minus 1 to plus 1, and there is no graph in between. Okay, so so this is y-axis. And between minus 1 and plus 1, this is minus 1. This point is plus 1. There is no graph in between. And there is nothing on the negative side, so I don't need this part. And what else do I have? I have these things go over there. So I have this thing, pi over 2. So why did I have? So this is not, everybody is sleeping today. This is not pi. Is it pi? Why am I getting this? This is, okay, so this is pi over 2. And this is pi, okay. So I have this line, okay, so I have this line and this line, so I have to draw them. Okay, so this line is pi over 2, this line is pi. Okay, so between this axis and that axis, so this, first of all, this one, because this one goes here. Okay, so it is increasing there, right? Because it is coming from here and it is going up to here. So this is the graph. And what happens to this one? It starts from, so this thing comes here. It starts from here. So this becomes x-axis. It starts from x-axis. It increases to this line. Okay, so it is like this. Okay, so if I'm not mistaken, this is what should happen. Okay, so this one, well, if you flip this, you get that. And it is between these two, so those two things flip over here. So this is y equals arc secant x. This is x, this is y. Okay? And when we calculated the derivative of this, you see, you take this is y equals arc secant x, if and only if x equals secant y. We know the derivative of secant, etc. When you put those things in, we found the following thing algebraically. Again, I'm leaving the sign part out. I have 1 x square root x squared minus 1. Okay, so at the end points, at the beginning, at this point and this point, this gives 1 over 0. So that means these are horizontal, these are vertical here. So let me do this like this. This is vertical, this is vertical. Okay, that is because the graphs here are horizontal. The graphs here are horizontal. Okay, so this will not hold. So this will not give me the tangent slope at this point. It is infinite. Okay. On the other hand, what sign of a square root I'll take? Here the function is increasing. It must be positive. When x is negative, when x is less than minus 1, this is increasing. So I need minus x here. When x is negative, I need minus x. Here it is increasing. Okay, so I need, again, this time I need x when x is positive. So I need absolute value of x. Okay? With my choice of secant, arcsecant is always increasing. That's the advantage I get. The disadvantage I get is I have to put absolute value here to show that it's always increasing. Okay, so in some books, I think Stewart also does that. He uses a different branch. You see, when you complete this graph to all of it, and then here for secant x, you have all of these things alternating. So you have to choose an arbitrary two arms of the secant x and invert them. Okay, if you choose this one, the arcsecant is always increasing, but you have to pay something. You put absolute value here. If you choose a different branch here, for example, you can choose this one and this one, then you don't have to put minus here, because on this part it is decreasing, on the other part it is increasing, and the sign gives you that already, so you don't have to put extra. So this is my choice, but you can make other choices. So when is this formula correct? Okay, we see that it is correct from minus infinity. So when x is less than minus 1 up to minus infinity, okay, and it is not x equals minus 1 will give me a vertical asymptote, and x larger than 1. So this is the range for my formula, and this is the range for the graph. Okay, so this completes our plotting the inverse trigonometric functions. Okay, now let's see if we can solve some problems. So I think I solved this tangent stuff. Okay, so now let's solve some problems, mostly from the book. Okay. So the first one, I did this last time, but we have to remember this. This is something which we use. This is one of the reasons why we did inverse trigonometric functions. If a is any number, I know exactly what this will be. This is 1 over a arctangent x over a plus c. Okay, so easy. Now that we know the derivative of arctangent, take the derivative of arctangent. So that's going to be, okay, so check the derivative. Okay, I have 1 over a, and this one from the formula 1 plus 1 over x over a square. By chain rule, take the derivative of this 1 over a. Okay, plus the derivative of c is 0. Now if you simplify this, okay, so here you see you will have 1 plus x squared over a squared, and you are going to multiply it by a squared. So this a squared in the denominator will go away, and this a1 will be a squared, and you will have in this one a squared plus x squared. So that's precisely what we wanted to have. Okay, so this is something that we keep in mind. The others are a little bit more tricky, so every time you need them, you can look it up from the tables. But this one is easy, so we keep it in mind. I think next week we'll start with the integration of rational functions, and this is going to be one of the crucial parts. Okay? If you have a polynomial over a polynomial, first you divide this polynomial by this polynomial, you get a polynomial that you can integrate easily. So we will be interested in polynomials of whose degree is less than the denominator. Okay? Then we have to find all the roots of this. We assume that we know all the roots. We factor them out. We will write them in terms of a number over x minus a number over x squared plus a squared, or well, that's all. Then we know. Then we can have either a number or x over x squared plus a. Okay, if you have x over x squared plus a squared, that's a logarithm. Okay, by substitution. The other one is arctangent. So a polynomial over polynomial, if you integrate this, will give you a polynomial plus logarithms plus arctangents. So, okay, that's what we will do next time. Okay, let's continue with another problem. So this problem says find y prime if arctangent of x square y equals x plus x y square. Okay. So this probably defines some curve, but it's not immediate to find the point on the curve. Okay. Because arctangent will be an angle. Okay, so here you need pi's, but it is not easy to see what arctangent is on some factor of pi. Anyway, we don't care about this. We take this as just an exercise. Find y prime over this. So clearly we'll use implicit differentiation together with chain rule. Okay, and the only reason why it is asked in this section is I have to know what the derivative of arctangent is, and I know what it is. Okay, so take derivative of both sides with respect to x. Okay, derivative of arctangent is 1 over 1 plus what you see inside squared times the derivative of what you see inside. This is 2xy plus x square y prime. So this is where I used implicit differentiation. Okay, so this is going to be equal to 1 plus y square plus 2xy y prime. Okay, so now I collect terms. Well, simplify, solve for, leave the calculations to you. Solve for y prime and find y prime. So you see here, y prime over this is a term containing y prime. You leave it there. Then this times this you take to the other side, and this you take to the other side. Then you take y prime outside the parentheses and divide everything on the right-hand side by the coefficient. Take a breath, simplify, and then you'll find the following. 1 plus x to the 4y square plus y square plus x4y, 4 minus 2xy divided by some other polynomial. Okay, so the only hard part is to go from here to here. Okay, and that's implicit differentiation together with chain rule, and you just implement the new knowledge. The derivative of arctangent is this thing. Question? X square y. Okay, you take the derivative of x square, which is 2x times y, plus now you keep x square, take the derivative of y. You don't have y square. Okay, so you just have y. And so this one, this is correct. Okay. Okay, so now let's solve something more serious. Okay, so here we have a problem. We have a figure like this. This is of length 3. And here you have, if it is 3, this is 5. And here you have 2. Then you choose a point here like this. So this is the point P. Okay, and this is the angle theta. Okay, so the question is find the position of theta, find the position of P to make theta minimum and maximum. Okay, so I can move this up and down. When this P is at this point, I can easily calculate what P is, because you see then I will be in this triangle. I will be in this triangle, and what will happen to theta will be here. Okay, so I can find what that is. And similarly, if I'm up above, then theta will be 0, right? So for this thing, we use these auxiliary angles. Call this angle alpha, or let me use my figure. I called the previous one alpha. So call this angle alpha, then call this angle beta. So we have alpha plus beta plus pi plus theta is pi. Is pi. Okay, so that's one relation where I put theta. The nice thing is I know what alpha and beta is. So let us call this distance x. One of them is going to be x. The other one is 3 minus x. So alpha is in a right triangle whose sides are known, and similarly beta. So I can write in this one, the easy thing is to write the tangent of this. I can also write sine and cosine of this, but for that I have to write this side in square roots. Okay, so nobody prefers to work with square roots because this is calculus. In a minute you'll take derivatives. Okay, so and the square root here will appear in the denominator. Okay, so this is old-time ancient considerations. Nowadays it doesn't matter. You just type it into a software, tell it to take the derivative, and you have the derivative. Okay, but these are old habits. We try to do this as simple as possible. Okay, so here in this picture, in this setup, alpha is equal to tangent of alpha is 5 over x. So alpha is arctangent 5 over x. Okay, so this is x here. Arctangent 5 over x. And beta is arctangent 2 over 3 minus x. Okay, and I have this equation. Okay. So we have theta is equal to pi minus alpha minus beta. Okay, so that is equal to pi minus arctangent 5 over x minus arctangent 2 over 3 minus x. Okay, so I have an expression here, and this expression, I see that this expression makes sense for all values of x except when x is 0 and x is 3. Okay, but all values of x does not make sense in my problem, because in my problem I allow myself to move this p only between these two parts. Okay. Geometrically, the problem will have a meaning if I move p down here, but that's not what we are asking. Okay, so we are only asking to move p between these two vertical lines to this axis. Okay, so that restricts the value of x. X can be 0 in my expression, but here x will not be 0 because I have division by 0, and x will not be 3. So my expression for theta as a function of x is given like this, and the values of x which are relevant to our problem is strictly between 0 and 3. Okay, so once you set up the problem, the rest is easy. First take the derivative and then start thinking. Okay, so we take the derivative. So derivative of theta with respect to x. Okay, so this is 0 minus derivative of this is 1 over 1 plus 5 over x squared times derivative of 5 over x is minus 5 over x squared minus the other one, 1 over 1 plus 2 over 3 minus x squared times derivative of this is, well, just 2 over 3 minus x squared. Okay, this has power minus 1, so I have minus 1 here, but after I take the derivative, again by chain rule, I take the derivative of inside, which gives me another minus, so I have plus here. Okay, so this is the derivative, and now you have to simplify it. So to save us time, let me simplify it. Okay, so here you see I have x squared here, x squared comes here, those x squares cancel, etc. So I have this minus cancels with this minus. So I have the first expression is plus, this is 5 over x squared plus 25. Here I have this minus. Again, this square will cancel with this square. So the second thing will be 2 over 3 minus x squared plus 4. Where is 4? Why? I have this 4 here. Okay. Okay, so this is the derivative. Now I want to equate this 0. Equal to 0 for critical points. The derivative is always defined. You see that there is no value of x which gives 1 over 0 here because I took squares. Okay. So the only critical points are the minima, maxima, or inflection points if they exist. So when you solve this, okay, so this thing is equal to this thing. So you multiply this by this, it is equal to this times 2. You collect terms. So so let me say theta prime. So this is theta prime. Theta prime equals 0. When you simplify this, you'll get a polynomial. So let me write just the last. After you simplify, you divide by 3. Everything has 3 in it. Okay, so 5x squared here and another x squared, so you'll have 6, etc. So let me just keep these things away. After you simplify everything, you'll have this. Plus 5 equals 0. Okay, so this gives us 2 roots. Roots are x equals 5 minus, okay, so let me write first plus 2 square root 5. So this is approximately equal to 9.47 something. So this is not in the range, not in our domain. Okay, so that means if I take p away, there is a critical point, but we don't want that. The other one is with the minus 1, x equals 5 minus 2 square root 5, which is approximately 0.5, 0.527, etc. So this is in our domain. So this is the, so it will be somewhere here. So this is the critical point. So check from, so this one is x minus this root times x minus this root. So if we write this 1, 2 like this, you will see that this is x minus x1, x minus x2. Okay, you want to see this polynomial like this, and okay, so that maybe that is too involved. It's easier to check what happens here. Okay, so just check the signs. Check that. Okay, so you check what happens when x is less than this and larger than this. Okay, check that in our domain. So I did that. Theta prime is negative when x is larger than we call this x2, and theta prime is positive if x is less than x2. So this means that if you start from x equals 0, the function is increasing. Theta prime is positive. The function increases and then decreases. Okay, so then this must be maximum. x2 gives the maximum value of theta in this domain. Okay, so what remains is to look at the minimum. So we take the limits of this as x approaches to the endpoints. That's another place where we use our knowledge about the graph of arctangent. Okay. So remember the graph of arctangent. So for the endpoints, recall the graph of arctangent. Okay, so it was something like this. So now we can be very rough. So this is x, this is y. I'm writing arctangent x. This is pi over 2. This is minus pi over 2. And the graph is something like this. Okay, so I calculate limit as x goes to 0. Okay, but x will go to 0 from above. X will always be positive. That's important in understanding the behavior of the behavior of arctangent at the endpoint. So I put plus here of theta of x. Okay. So what was the formula? So this is pi minus limit x goes to 0 of arctangent 5 over x minus limit x goes to 0 arctangent 2 over 3 minus x. Okay, so now this is becoming infinite. Okay, so x is becoming infinite. But the important thing is x becoming infinite in this direction or in this direction, according to which arctangent will be plus pi over 2 or minus pi over 2. So that's why I paid attention at this point that x is positive. So as x is going to 0, 5 over x is going to plus infinite. So on this axis we are going to here and we are looking at the graph of arctangent. It is going to be pi over 2. Okay. So this is pi minus pi over 2 minus. Now arctangent, you see, is continuous in between. So you can take it inside and this is going to be 2 over 3. So somewhere here you have 2 over 3 and this is the value of arctangent. So it is just arctangent 2 over 3. Okay, so I calculated this for you somewhere. This is approximately, okay, you subtract pi over 2 from this and this. This is approximately something and you change it to degrees, 56 degrees. Okay. Then we do the same thing with limit x goes to 3 from below. Okay, so this time theta x. Okay, so let me finish this and then we can stop. So this is minus limit x goes to 3 minus arctangent 5 over x minus limit x goes to 3 from below arctangent 2 over 3 minus x. Okay, so I have pi here minus, this is continuous when x is going to 3. Okay, 3 is somewhere here. So x is approaching here, no problem. You just take this number. So this is arctangent 5 over 3 minus, okay, now this is becoming infinite, but x is always less than 3. So this is always positive and going to 0. So again, this is going to plus infinity. Arctangent of plus infinity is pi over 2. And when you calculate this, what did you find? 30 degrees. This is approximately 30 degrees. 29 something, I think. Okay, so we know that this is the minimum. This gives the minimum. Mean value of theta at the end point. We don't need the value of exactly the value of theta at the maximum point, but because we know that it is the maximum point. But just for curiosity, so what was this? We also check theta at 5 minus 2 square root 5 is approximately 57, I think, 57 degrees. Okay, so in fact, y equals theta x for x between 0 and 3 is something like this. So it increases a little bit and then goes down to somewhere here. Okay, so this is 3x, this is y equals theta x, this is theta. Okay, so it starts from theta, this is theta. Okay, so here theta in degrees in this graph. So this is 56. So this part is 57 and this is 30. So this is how the function theta behaves in our domain. Okay, so we can stop here.